Okay, so let me talk about the second law and the third law of thermodynamics. First, let's focus on the second law, which is really the heart of the thermodynamics. This second law of thermodynamics is about change. Okay? It's about change, and there are two historical statements that has made it, and it is, I mean, this is a very old one that has been doing, and if you have a heat converting to the work, I mean, this is something that people start to question a lot, because when you burn, you think about the steam engines, you heat it up, and you're moving the vehicles, you're moving the locomotives, and can I get the maximum work? What are the work can I get out? Is it actually 100% conversion? Is it possible? Okay. The old Kelvin statement is, no, you are not going to get 100% conversion. So there's always issues on the engine efficiency, and then this is naturally the Carnot cycle, which is Carnot engine, is come about, and that actually became the birth of the entropy. He's the one actually who discovered the Carnot cycle, who wrote the thesis by the French scientist, and he really essentially supported. We need a new the state function, and that is, well, let's call it an entropy. Okay, I don't think the Carnot even used an entropy as the one, but he's the one that suggested. I mean, this is a sort of the very easy to understand parameters, and this one is much more relevant. Is a heat under constant pressure. We have called the reaction heat, and this is something that we can measure, and so on. If you use a bond calorimeter, this is something that we can measure. But this is something that we're going to discuss shortly after, but that's an entropy, that state function that we're going to do. Once we combine these two and the entropy, we're going to have these two different types of the free energy, and because of the constant pressure scenario, Gibbs free energy is much more common to focus later in the chapters. Helmholtz free energy is some constant volume system, the free energy that is kind of comparable to the Gibbs free energy. We want to shortly discuss that as well. Clausius statement is another one. When I have a high object, a high temperature and a low temperature, cold temperature, okay? The heat always flows from here to there. That's his statement. I don't think that is also, we probably know, but it is not, it's about how the things are happening, right? So the direction for changes is that they start to make a statement. The most useful statement is, we're going to talk about S, and if you're looking at the total entropy of a system, the direction for change is this, and there is a little line there that means it's 0, and delta S total is 0 when reversible process is reversible. So reversible means there's no direction, it's going back and forth. So in a way, that's the system at rest in peace. That's what we call equilibrium, right? So that's what we call equilibrium. And I don't think that most people would want to find out where total entropy of your system plus surrounding is changing to 0. That's the equilibrium position. We don't want to do that, but this is one statement that we're going to deal with in this class first. And this most important, most useful is actually this one. Okay. The last one is the even more useful one. Do you know what it is? Right? Delta G is in a direction for dropping, right? It's not going up. It's always coming down. That's a spontaneous. And what that means is delta G is 0 at equilibrium, and this is something that we're going to do a lot, and this is equilibrium constant, decay, and their temperature dependence and so on. This has been covered a lot in the one. we are essentially whole thermodynamics. You start from the energy conservation, understanding the concept of entropy, and then focusing on the Gibbs free energy. That Gibbs free energy is going to allow us to understand the chemical potential, equilibrium, and all these thermodynamics of phase transitions, liquid solid transitions, solid liquid transition. We all can know this. So really at the heart of this is this one. Okay. So what is entropy? So I will just give up the definition. Okay. Change in the entropy, just like a du, okay, is Q reversible divided by temperature. That's the definition. Sometimes they're useful, sometimes they're not useful, but this is and sometimes, and this textbook, for some reason that they use Q with a D, so you always free up your mind. Q is actually change itself. dq is the same as a Q. Just keep that in mind. There's a huge difference between ds versus s. S is a state function itself. This is a change in the s, whereas this is a dq reversible. What they meant was q reversible. Okay? So it is a heat transaction on the in the reversibly, and that's the definition. This is the B definition. And this one came out from not from nowhere, but it actually came from the simple understanding of the Carnot cycle, which is I hope I can cover today. So therefore, okay, so if I have a change in the ds, initial state to final state, I guess this is we call delta S, and then must be the initial state to final state T over Q reversible. So it's a matter for us to find out Q reversible in this. So that's one thing that has been done. And the second one is, so I want to give a clear distinction between the system entropy versus surrounding entropy. So when you write S, that means I'm talking about system entropy. And if you want to talk about surrounding or the total entropy, is a combination of system and everything else. So that's another definition here. Therefore, to me, the most two useful equation is this. Reversible change occurs, and irreversible change means actually that's a spontaneous. You're not going back, right? Spontaneous change, and you're not going to be back. Whereas the things are reversible, and that's the one that. And believe it or not, actually, you can tackle this problem for a limited, well-defined case, and let me walk through it by by writing a table here. Okay, so